All right, thanks a lot, Tibor. And in fact, I am going to flash back a little bit to Tibor's earlier presentation on the SAVE seismic concept, because VBOS is related. It's, I would say, a younger brother, perhaps, of SAVE. If you can go to the next slide, please. VBOS was born actually thinking about Venus science on the cheap in the year in 2017 in the context of a discovery selection in which there were two very competitive Venus missions that were not selected. We got a question from the NASA deputy administrator, can you develop a Venus mission for less than Discovery, for say a $200 million cost cap? And the mandate that was, we didn't know the answer to that at the time, and so we got a little bit of incentive and support to study this. We had science goals directed from the then current Visions of Voyages Decadal Survey. We had a launch year targeting 2025, and we were also targeting a lifetime extended stay on the surface of 120 days, reminiscent now of what Tibor was talking about with SAVE, for a long duration landed platform. Next slide, please. This is the study team. It was a Glenn Compass run. A parallel study was done actually at JPL as well, where they looked at a whole bunch of different solutions. And the difference between the two was that the Compass run came up with a single point study all the way through, which is what we're going to see. So next slide, please. So the mandate: design a reference mission for a $200 million lander orbiter pair to be delivered sort of as a secondary payload launch. The orbiter, like an ESPA ring or some such, the orbiter carries the lander, deploys the lander with an entry, descent, and landing before the orbiter capture. The science would be conducted by both lander and orbiter. Lander gathers infrared radiometry, temperature, pressure, chemical data during nighttime landing, and for a Venus night-day cycle surviving on the surface, wind and weather data from the surface, and with sort of regular 2-minute transmissions of data every 12 hours. The orbiter takes IR images coincident with lander IR radiometry, data uplink and relays to Earth, and potentially other orbital science packages as well. Next slide, please. This is sort of our science matrix that we came up with for the study. I won't go too deep into it, but there's orbiter, remote sensing science, and there is probe, both descent science as we descend through the atmosphere in sort of a mini Da Vinci approach, and very, very mini Da Vinci approach, and landed science for long duration observations on the surface, with a variety of high temperature, low power, low data rate, and low mass instruments. Next slide, please. I don't need to tell you at this point about the harsh environments that we have to deal with, both in the descent and the surface environment. Just suffice to say that the descent vehicle would pass through all of the different atmospheric layers, looking up and down with its radiometric sensors, sniffing with its chemical sensors, and then existing at the high temperature pressure conditions of the surface for many tens of days. Next slide, please. Here is a view of the lander and the various components it contains. If you just look at the upper right, it's small. And the lower right, it's got the drag plate, which is about 40 centimeters across. The cube sort of center, which contains the battery and the comms, it's less than 8U essentially of space. And it's got a wind sensor that sticks up. It's got a UHF antenna. It's got bolometers that point up and down. The drag flap is also sort of its antenna substrate. And underneath, it's got reaction chemistry for the surface, pressure and temperature suite. And inside, it's got its high temperature electronics interior and its high temperature battery, which comprises most of the mass of the lander itself. And this is a direct descendant of the LISSI demonstrator that Tibor talked about as well, which has had a number of tests, functional tests, in conditions like in the gear chamber, and has had many components already in experimental stages. So next slide, please. The lander itself in this envisionment is 15 kilometers in mass, about 20 centimeter on the side cube with a drag flap. And so it's really, not that much bigger than a very large hat. If you go to the next slide, we can see the EDL configuration. Again, that system is also very small, and in the way we went through the exercise, we were talking about a heritage aero shell, 0.5 meter, passive separation systems, and the lander itself provides telemetry. So next slide. This is our orbiter component. It's basically a small set. It actually resembles, even though a couple of years ahead of time, it resembles kind of the Lunar Trailblazer platform, a small sort of 1 meter-ish cube, deployed some antennas. It's got a UHF antenna for communication with the ground system. It's got a few instruments, primarily near-infrared imager and radiometer package, and potentially some other very small low swap instruments as well, communication system for direct to Earth, and again, essentially a small sat for a multi-month duration in Venus orbit. Next slide, please. It has about a 200 kilogram wet weight, with about a 90 kilogram monopropellant to provide burns. At Earth to captured Venus, about 1 kilometer per second total delta V, 200 watt solar arrays, UHF uplink, and X-band data return to Earth. Next slide, please. And this is sort of our CONOPS. Once we deliver the spacecraft to the surface, we're talking about, again, not putting it in a challenging environment. So the plains of Venus are basically the target environment. We land at night. So on the descent, our bolometers look both down and up in a couple infrared wavelengths to determine, to measure the upward and downward radiation from the atmosphere, while the orbiter is looking down from above in the same IR channels as well as a few more, so that we can do this concurrent upward and downward passage through the atmosphere, measuring the change in radiance as we descend through the different levels of the atmosphere. Once we arrive at the surface, the gas, pressure, wind, temperature sensors are constantly on. They're really simple, small voltage sensors or current sensors that generate a couple bits of data that is basically directly uplinked to the spacecraft whenever it passes over by a timing circuit or something similar, and in a sort of dumb way. The lander just sends it up when the spacecraft is there. The spacecraft listens, gets the data, relays it to Earth, and the battery will last for 3,000 hours or about 120 days, meaning that if you land at night, then you experience the change of conditions, primarily illumination conditions, from the night side to the day side. This concept of the landed system does not have a camera itself. We don't have at the moment cameras that are small enough mass and high temperature to not require either some sort of thermal protection system. And so this initial concept does not have any kind of camera system, which is another reason why it's okay to land at night. So day-side operations are essentially the same. The concurrent upward and downward looking of the radiometers, bolometers on the spacecraft and lander continue during the day. And if there are any changes in the winds, if there are any changes in the chemical sensors, those things are relayed as the measurements continue over the course of these 120 days. Next slide, please. So, the science value of this prospect, it's based on duration. And the path we chose was simple instruments measuring periodically, sensing the environment for this entire duration on the surface of the Venus night to day cycle. The lander and orbiter work as a science team, where the orbiter is more than just a relay. This IR sensing tie between the lander and the orbiter adds value, especially while you can look up and down at the same time. And Giada and others have referred to the fact that the signals coming through the clouds differ depending on where you are and what you might be sitting on. There's an alternate path where you can shorten the life to tens of hours of continuous science, but at the expense of duration. Next slide, please.
A little less than 2 minutes now.
Yep. So this is a list of the technologies kind of at the time of the study and a little bit more advanced. We have our communications, we have our high temperature battery, we have the entry system, we have all the various types of sensors which are in various stages of development. We have our radiometer bolometers, and we have our reaction chemistry sensors, which are all in various stages of study, and some of which have spent some time in the gear chamber or are going to in the next year or two. Next slide, please. Very quickly, the mission design: you launch on an S-ring, you fly to Venus, you pass, you let the lander off on the way out, and it descends, and then you break into orbit and have this regular sort of daily uplink from the lander as you and relay back to Earth as you go around the planet for the duration. Next slide. I think I'm coming up on the last couple. The cost, $200 million cost gap was very restricting for an orbiter and a lander, as you might expect, and it could be done with the caveats of a free secondary launch. And that the science data at high value is small to keep the costs down, and that it assumes that Phase E and Tierra and technology development was not part of the cost. And we came in at $201 million when we ran everything together, the cost split of about 70-30 from the orbiter lander. Next slide, please.
So we're just about out of time here.
Yep. I think we're here at the end and the conclusion. The conclusion was that in 2017, the answer was we could almost do it for $200 million in the cost cap. In 2023, actually, it's gotten potentially easier with small sat development in the last couple of years, especially, again, like with Lunar Trailblazer as a platform, those costs are likely going down. And what is the worth of this kind of an exercise? And what we've heard before, and we'll hear, I think, even the last couple of talks, multi-asset missions are one of the real directions for ongoing future Venus research. So along with the super capable large missions, these small multi-asset, multi-location, long duration missions are part of the future paradigms of Venus exploration. So with that, I will say thanks and on to the next.
All right, thank you, Noam.